Okay, so AP Chemistry. It's kind of exciting. Well, in the fall I had to teach Chem 1 honors, so which was a good class, don't get me wrong. But I've taught like Chem 1 honors for like 6 years. And so I'm used to all of you coming in and knowing like, oh, mole conversions and atomic structure, and it's like, what do you mean you guys don't know what a mole is? And so, yeah. So now I had to now I've got to like recalibrate and go, oh, you guys know what's going on, and it's cool. So now here's I say that, but I know you all come from like vastly different chemistry backgrounds. Like some of you just came straight out of Chem 2. Some of you took Chem 2 at A South. Some of you have taken Chem 2 maybe like a year ago. So here's the assumption that I'm going to make, that you all don't know anything. Okay? So that's the assumption I'm just going to make, and then we'll just build from there. So for some of you that that are familiar with my kind of classroom policies, that are for those of you that aren't, basically I have 2 classroom policies. Learn what I teach you, and don't irritate me in the process. Okay, that's basically it. And so among the long list of things that irritate me are cell phones. So for those of you that have me, you know your cell phones go up there in the holder, and I don't do that to be a jerk, okay? I do that because there is no way for you all to be in the moment at this level of class, and it's a tough class, and worry about what someone texted you or whatever, why your phone went off, maybe your TikTok video, which is a plague on humanity, but whatever that may be. And so my phone will go up there, okay? I won't have my phone on me. My phone is always going to go up there in the first holder. So, and I've got a simple contract for you to sign. For those of you that have already signed it, don't worry about it. For those of you that are new, it basically says, hey, I know that out of respect to everyone in the class and myself, I want to put my cell phone up there. I'm not going to count them, okay, and go, oh, you know, are there 16 cell phones up there? I'm not going to do that. Now, if I look up and there's only one, okay, yeah, and it's mine, there's going to be an issue, okay? But just take your cell phones, put them up there. It's a fight that I don't want to have to fight, mainly because you can't do it. I mean, you all think, oh, I can multitask. No, you can't, okay? As soon as that cell phone goes off and it vibrates and you know it, immediately your mind goes someplace else. And to be successful at this level of chemistry, we need to be on the same page. So there's that. In terms of your grade, 60% is tests, 20% is homework, 20% is labs. When we do labs, they tend to be like multi-day labs. Like the very first lab you're going to do is actually going to take us like 3 days to do. And when we do labs, we're going to go next door to that room next door. So that's what we're going to do all of our labs. And quizzes, and this is for those of you that have had me for physics. I approach chemistry a little bit different, mainly because this first unit it's one of the biggest units we're going to have. It's on equilibrium, and we're going to deal with like acid-base equilibrium and solubility and things like that. And so the first big blown test is going to be about 3 weeks out. And I don't want to wait 3 weeks to have like this first assessment. So next Wednesday, okay, is where we're going to have like the first quiz. And so that's what's going to be different. In physics, it was always just the big test. In chemistry, I need to kind of keep more of an update on how you're doing. I don't want to wait until 3 weeks in and go, wow, you all can't do equilibrium and this is bad. And I find that out when we take the test. And so that's why I do that. So in the back, let me kind of get you sorted on the bookkeeping things today. So for those of you that have had my physics classes, you'll recognize this concept. This is a sheet of equations that you will have, and this is the green sheet, and this has all of the things that we're going to do throughout the class. There's some equations that I add to a particular topic, like for example, we'll get into what's known as the Nernst equation when we do redox reactions. But I will never make you memorize the equation. So if you ever need an equation that's not on the sheet, I will give you that equation. So what will happen is I'm gonna give you this, and then when it comes time for the test, what I will do is I will give you a laminated version of this. So you always have this available to you, you just have to know how to use it. You're also going to have a periodic table, okay? So what's unique about this periodic table relative to the Chem 1 and Chem 2 periodic tables is that it only has the symbols, it doesn't have the names on here. Because this is, for those of you that are going to take the AP test, we'll talk more about that later if you do or you don't. This is the table that you will have on the AP test. And so hopefully by now you all know that C is carbon. And you're like, oh, you never knew that. Wow, okay. Your chemistry teachers did not do you a solid then. So this is the periodic table you have to get used to using. And I'm never going to pick anything weird like, you know, tungsten or the ones we're going to use are going to be the most common elements. I promise you, I'm not going to pick some obscure element that never gets used and say, oh, I'll be a jerk and I'll put that on there and I'll see if they, no, okay? The ones you're going to use are going to be very, very common, won't be anything weird. Now, on the back of this is a standard reduction chart, which we will spend a lot of time talking about once we get into redox reactions, which will be the second big unit that we do. This basically tells you, hey, is a reaction going to take place? Is it going to gain electrons? Is it going to lose electrons? Well, for now, don't worry about this. Just worry about this. The other thing that's back there is that you're going to find this sheet of paper. Basically, this says, hey, this is what's going to happen in AP chemistry. And kind of gives the background, what we're going to do, whether kind of a brief explanation about whether or not you take the test. And that's a decision you're going to have to make relatively quickly. And the cool thing about the AP chemistry test is that depending upon which university you go to and the score that you get, you can actually get out of Chem 1 and Chem 2, depending upon your score. Like if you get a 4, like at K-State KU, you get out of Chem 1 and Chem 2. And if you get a 3, they might give you Chem 1. So that's a policy. What you would have to do is go to, you do any kind of Google search and just go, hey, type in Kansas State University, for example, and AP chemistry credit. And there's links there that it's going to tell you, hey, this is a score that you have to get. Scores on the AP test range from 1 to 5. Last year, none of my kids got below a 3 on the test, so odds are you're going to do pretty well on the test. So, like, literally everybody got a 3 or above. So that might sway. It's like, oh, I don't know. It's like, well, if history is a predictor of the future, you're probably going to do pretty well. Also, you're going to have this sheet. This is just more of a reference sheet. It lists all of the anions and cations, strong acids, strong bases, weak acids, general information about organic. No, I'm not going to expect you to memorize this. Don't flip out. It's like, oh, we have to have all these memorized. No, you don't. But here's the one thing I am going to expect you to memorize. This is the one thing. Up here, in this top left corner, there's a list of strong acids. And there's strong acids and weak acids. And we'll talk about this. It has to do with how well they ionize. Strong acids completely ionize, weak acids don't. Okay, and that's gonna be the whole basis of what we're gonna do in this first unit, is this whole concept of strong acids, weak acids, and what that looks like. So the only thing I'm going to ever really expect you to memorize is this list of strong acids and the formulas. So like on this quiz coming up on next Wednesday, of these 7, by next Wednesday, you need to know 4 of them. You need to know their names and their chemical formula. But you already probably know a lot of them, like hydrochloric acid, O, HCl, nitric acid, HNO3, hydrobromic acid, HBr. So sulfuric acid, H2SO4. So you probably, right now, know at least 4 of them anyway. So that isn't going to be a big deal. If you're really into like flashcards, make some flashcards. Write the formula on one side, write the name of it on the other side. That's a simple way to. Do flashcards speak to you?
Yeah.
Okay. All right. There you go. There's your first chance to do flashcards.
Awesome.
Okay, cool. So what you'll notice is there's a lot more weak acids than there are strong acids, and this is not the whole list of weak acids. This is just the ones that are most common. And again, I'm not going to expect you to memorize, oleic acid is C18H34O2, okay? No. Wow, we have to know all of these. If you want to, that's fine. Okay. Switch it up here. Then this one is, if some people like this is basically all of the big topics that we're going to cover between now and the middle of May. So there's that. This is just one option. There's a whole bunch of different ways you can look at solubility rules and net ionic equations, which we'll talk about. But this is just one representation of solubility rules. And that's kind of that's going to be one of the things that we're going to have on this review assignment is net ionic equations. And that's when, and again, hopefully you know net ionics. If not, I'm going to assume that you don't, and we're going to figure all that out, and we're going to do a refresher on it. So this is a list of solubility rules. There's also solubility rules in your textbook. You can also get on the internet and type in something and see if it's soluble or insoluble. There's any number of resources. I'm not going to expect you to memorize all the solubility rules, but there's certain ones that you're just going to know, like nitrates, for example. All nitrates are soluble. All group 1 elements, lithium, potassium, sodium, all of those are soluble, okay? Those are just kind of generic ones, but I'm not going to expect you to have memorized all the solubility rules, but it is a resource that you need. On the back side, there is a reactivity series. Basically, that tells you if a reaction is going to take place. Typically, when you put a metal in with an acid, for example, you all have done that, where you take a, let me see, that's weird. Okay. Like I'm guessing at some point you all have taken a beaker of hydrochloric acid, for example, and you drop in a piece of magnesium and it starts to bubble, and you collect the gas and make it pop and all that good stuff. So magnesium is more reactive than hydrogen, and so therefore the reaction takes place. But if you take silver, which is why we use silver in jewelry, and you put that in hydrochloric acid, nothing's going to happen. So this is just a reference here on the back. So right now, there should be, go back there, here. So go back there, you're back on the center table, just go down the line, one of everything.
This is like a whole novel.
Oh, you haven't even seen the review assignment.
Yeah, you didn't give us pre-semester packet.
You're right, I didn't.
Just,
what
do
this
you
is.
usually?
I don't remember
No.
anything about chemistry.
Look at this survey.
I'll do that with you, Gracie, but not for a grade.
Oh, you're gonna mess me up.
No, it's because my house went. And then they were like, because I was the one that popped out. Oliver was the one holding it. I was the one that popped it. My ears were ringing. I couldn't hear. We're talking about when Stockholm like blow stuff up in her classroom and our ears rang.
You what?
She let us like explode stuff on the table and then our ears
Blew up
started
a
ringing.
pumpkin one time and it hit a girl in the face.
Yeah, I did. Yeah, it was bad.
Who is that?
Miss Stockholm.
She used to teach right next door.
I love her section. That's all I
Her last semester she didn't teach very well though.
Maybe it's
Sorry,
already
Miss
gone.
Stockholm. She was ready for retirement. She was ready for retirement. She was so prepared to be done. So ready.
Because we were still there. I know the thing where she like shared a little bit.
On what?
And then like she heard
Really?
it and she was like, let's do it.
Okay. Oh,
This semester, like, let's do that.
that's weird. I thought I ran enough off for. Okay.
Oh, I didn't mean to do that.
I just had like an instant.
I'll put that later. No, I just grabbed 2 of them.
Okay. All right. So let's go, and again, here's the disadvantage from my perspective that I got to figure out where everybody's at. So we're kind of going to start at the beginning. So, if you look at kind of the challenge that I face, is that teaching and learning is, you can make the analogy that it's like a wave, okay? And what I've got to do is, I can't put the material so far out in front of you that you get bored, or that it's like I can't understand this, and then you check out and it's like, oh, this is too tough. I can't make it so easy that you get bored. That doesn't work either. Then I get bored and bad things happen. So I just kind of have to keep you challenged, but yet working within a confine of the existing knowledge that you have. And so, you know, it's been said that teachers never teach anything, and I've been doing this for a long time, and I never have. But no, and you're sitting there going like, oh, gee, yeah, it's a waste of taxpayers' dollars. And no one ever has taught you anything. What's happened is that I've presented the information, I've challenged you, that you make that decision that says, wow, this is something that's worth learning. So I'm guessing most of you are going to be doing like pre-med, pre-vet, engineering, something like that, right? Okay. And so I applaud you for taking this class, mainly because you talk to my kids that go on to K-State, KU, whatever. And, you know, I'll say, hey, how was chemistry? Like, I showed up for the tests, and that was it, you know, because you guys are gonna know so much going in, and that gives you a huge advantage. Even if you don't take the test, you can go up to K-State, KU, take Chem 1, and it's gonna be an easy A for you. And so therefore you can like shift that time and those resources to studying for the other classes that other kids that don't have to, because you're already gonna walk in with that core knowledge. But here's the thing that I have that's more challenging than teaching physics, is that physics is very visual, okay? You know, we talk about gravity, okay, cool, right? Forces, right? Hurt, okay? Make something speed up, slow down. Here's the problem with chemistry, is that we're going to spend the next 18 weeks together talking about things that I can't show you, okay? We're going to talk about electrons and protons and neutrons and the nucleus and how things work. And I can't show you a picture of a single electron. So to give you some idea of kind of the magnitude of this and how small things are. And so here's a sheet of aluminum foil, okay? That's it, one sheet. And if you were to look at just the thickness of that aluminum foil right across here, okay? If you were to stack up those aluminum atoms, there'd be about 94,000 of them just across this dimension right there, okay? Not the whole, not all the way across, that's just the thickness, 94,000. Stacked side by side by side by side by side. It's a lot of them. So what that means is that atoms are incredibly small. And so not only are atoms incredibly small, then you have the subatomic particles. So what are the three primary subatomic particles in an atom?
Protons, neutrons, and electrons.
Protons, neutrons, and electrons. If we're talking about solids, we would throw in protons, okay? But we're just talking about atoms. So the protons and the neutrons, those are found in the nucleus. And they're important. That's what creates mass, okay? But that really isn't going to be the point of the story. If you were studying nuclear reactions, hey, would worry about the nucleus. In chemistry, we would worry about what's happening with the electrons. But here's the anomaly that came out of the results when they began to study matter. And for some of you might remember this, there was a guy by the name of Ernest Rutherford. And Rutherford did what was known as the gold foil experiment. And he had a box and it had a radioactive source, and it would go through a radioactive decay and it would shoot out alpha particles. He called them alpha particles because he didn't know what they were at the time. Turns out they were a helium nucleus. Now let's make sure everybody knows when I write this down, because part of of chemistry is that it's like, almost like a foreign language. So I have to make sure everybody understands what that language is. So when I put this 4 up here, anybody remember what that 4 represents?
Like the total number of particles in the nucleus.
It's called the mass number, right? Sometimes you'll see the protons and neutrons referred to as nucleons. So that's what's contained in the nucleus. So you have 2 primary particles in the nucleus. You have protons and you have neutrons. So this says that if you were to look at the nucleus of this, there would be 2 protons and 2 neutrons. This number here represents the atomic number. So one of the things you want to look at is that the sole thing that determines the identity of an atom is the number of protons. You can change the number of neutrons, you can change the number of electrons, but it is solely the number of protons that determines the identity of an atom. So when you look at how your periodic table is arranged, 1, 2, 3, and then across, it's arranged by increasing atomic number. So you can alter the number of electrons, you can alter the number of neutrons, and those are what we call isotopes, because remember, if you remember your terminology, okay, isotopes have the same number of protons, but they have a different number of neutrons. So you can think of protons and neutrons as being like, kind of like St. Bernards and, I don't know, whatever, big sheepdogs, whatever, okay? So they hang out in the nucleus, but they just kind of chill out and play, okay? They provide a lot of mass, but they really don't do much, okay? They're just kind of there, they're clumpy. Now the electrons are like the chihuahuas of the atomic world, okay? If you've ever been around chihuahuas, God bless you if you have. But they're these yippy little guys, yip, 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 okay? And we can manipulate them. And so the electrons, because they're so small, they create volume. So what happened is that Ernest Rutherford shot these alpha particles. He didn't know what they were, because at the time we didn't even know the element helium existed, because the element helium comes from the Greek word helios, which means sun. The first place we actually found helium was the atomic spectrum of the sun, and we found an element that we had never seen before. We said, oh, it's in the sun. That's helium. Helios, we'll call it helium. And so it shot out these particles, and the particles, for the most part, went right through the gold foil. And everybody's kind of like, wow, that's kind of weird, okay? Wow, what do we do about this? And so they figured out, because these particles basically went straight through, that the gold foil, which appears solid to us on a macroscopic level, on an atomic level was mostly empty space. And so if you make like a football stadium, if you've ever been to like Arrowhead Stadium or any of the big football stadiums, if you consider that to be like an atom, the nucleus is basically a baseball in the middle of the 50-yard line. That's where all the mass is. This whole space around it is occupied by the electrons. The electrons are what give it volume. But it's the interactions of these electrons that allow things to bond together. So one of the great mysteries is that how do you explain this? And so one of the things you'll hear me talk about, this plays out even more in chemistry than it does in physics, is that Mother Nature is a lazy prima donna. Okay, so when we study chemical reactions, any chemical reaction is going to take place because Mother Nature gains something from it. Mother Nature doesn't gain something from it, Mother Nature is not going to allow a chemical reaction to take place. So if I take magnesium and drop that in hydrochloric acid and the reaction starts, it's because Mother Nature gains something from it. If I take a piece of silver and drop that in hydrochloric acid, nothing happens because Mother Nature goes, I'm good. Nothing's going to happen. I'm chilled out. So in my mind, Mother Nature is this kind of gray-haired, tie-dye wearing, has Birkenstocks, hits the hookah pipe, whatever. She's like, so, whatever, And so when we study chemical reactions, and that's kind of what we're going to do, it's kind of chemistry what it does, is that when you see a chemical reaction taking place, it's because Mother Nature gains something from it. And if she doesn't gain something from it, Mother Nature goes, not going to do it. And so you can also make the analogy of like an energy. So that, like if I roll this ball across, oddly enough, it falls down. Okay? So if I can't find my golf ball, it's like, oh man, I lost my golf ball. Okay? I'm not gonna look up here because it's not gonna be there. Because Mother Nature goes, it's way too high in energy state. It's not cool. Mother Nature goes, oh, we'll put it at the bottom of the energy well. So Mother Nature always wants to settle at the bottom of the energy well because that becomes the most stable arrangement. And so if you look at why chemical reactions take place, that's why. So for example, what's the most, if you take oxygen, okay, remember, and again, this is, I'm not trying to insult, I'm just making sure everybody knows what's going on. Remember the diatomics, they always, if they're a gas, they always exist as two. There's hydrogen, and then nitrogen, oxygen, fluorine, bromine, iodine, okay? So those always exist as binary atoms. So here's oxygen, and here's hydrogen, okay? And you combine these two, and you're gonna get water, okay? And a lot of times when we talk about water, we draw it, this kind of looks like Mickey Mouse, okay? We call it the Mickey Mouse molecule. And it exists as this form because this is the most stable. Which is H2O, right? Well, if hydrogen peroxide was the most stable form of hydrogen and oxygen, we would have oceans of hydrogen peroxide, okay? And it would rain hydrogen peroxide instead of raining water. But hydrogen peroxide is the most stable, which is a good thing. If you've ever had a cut and you poured hydrogen peroxide on it to fight an infection that bubbles up. Okay? And so if hydrogen peroxide was the most stable, it was like, oh, you got a cut. Oh, go jump in the water. You'll get rid of that infection. Okay? But it isn't. Water is the most stable, which is why we have vast amounts of water on our Earth, because that's the most stable arrangement, because that's like at the bottom of the energy well. So when you look at these electrons, and here's the philosophical aspect of it, is if you look at us being here at 12:25 on January 5th, 2023, talking about chemistry, it's weird if you think about it, like we're a group of atoms that know that we're a group of atoms, and we talk about atoms that make up the universe, okay? And one of the things that philosophical thing is that we're all made of stardust. So if you look at how the Big Bang started, pure energy, it's called a singularity. Something happened, the universe began to expand, it was all pure energy. We went through this process of what's called hyperinflation, and the universe expanded rapidly. And as it expanded, it began to cool, and the energy began to form into particles, okay? Electrons and protons and neutrons. And so eventually, and you've heard this speech already this morning, and so eventually there were some distortions in this distribution of mass. And so you had segments that got a little bit more intense gravitational field, and they began to pull in other matter. Because the simplest periodic table that ever existed was right after the Big Bang. You had hydrogen and helium. Oh, that was cool, right? Literally, it was a two-element periodic table, hydrogen and helium. Might have had a little bit of lithium thrown in just for good measure, but not much. So stars begin to form, fusion process, hydrogen combines to make helium, slight loss of mass, it produces energy, we have suns. So even then, none of the complex atoms that make you up, the iron that's in your hemoglobin, the carbon, nitrogen, oxygen that makes up your DNA, okay, none of those complex atoms existed after the Big Bang until that first generation of stars. And then even then, they had to collapse. Those particles got kicked back out. Then you started a second generation of stars. They went supernova, and that material got kicked out. And so all the complex atoms that make you up are literally stardust. They were all formed in the depths of stars that have collapsed, exploded. That material got kicked out, and then it got recombined, and here we are as a group of atoms talking about atoms. And it's kind of cool if you think about it. But electrons don't like each other, but yet they bond together. So here's a simple way to view this. And that's why I said statistically we really shouldn't be here, but we are. It's a good thing. So I got a balloon, right? And I've got, this is just like a piece of plastic, so give that so Zach can see this. I don't want to hear Skippy whine about anything. So I've got this balloon, and we're like this. Okay, cool. Right? So oddly enough, this is made of atoms and this is made of atoms. And so I'm gonna rub this. And so what's happening is that this is taking chihuahuas from the table or from the blanket. So this thing is negatively charged. Now then I'm gonna rub this on the blanket, okay? And it also likes electrons. And then I can do, unfortunately it also likes my electrons. It's problematic. So then I can let go of that. So I can make that levitate and defy gravity. But if I put my hand up there, it becomes attracted to my hand. But if I go back to doing this, oh, what's this? Is that a good thing or a bad thing? I'm not hip. I don't know what that means.
We were making fun of Stockholm and how she would probably have it like stuck to her hand, like couldn't
Or
even get it to
here.
levitate. Yeah.
Yeah, there's the trick to it. Yeah. So, okay. So here's the point: is that we exist, and we have these complex structures of DNA and skin and hair and blood and an atmosphere of oxygen and nitrogen. And we only exist in the form that we are because we get these atoms to link together. Well, but here's the problem. Okay, you look at a diatomic molecule like oxygen. Okay, well that's kind of cool. All right, so here's oxygen. So a quick refresher, if you look in the periodic table, you have the element oxygen. And so if you look at what you all have, let me see your periodic table because I remember the sequence that's written in. Okay, so here you have oxygen, and you have that number 8 above it, and then below that you have 16.00. So let's make sure everybody's cool with what that number means. So you have 8, right? So what does that top number represent?
Number of protons.
It's your atomic number. So this is the number of protons. So this creates a problem. When you look at what happened with Rutherford, Rutherford says, oh, you have this dense, very dense, positively charged nucleus. Well, what I just showed you is the fact that when you have similarly charged particles, they don't want to be near each other. Okay, I can make that plastic levitate. They don't like each other. So that became a huge problem. Is that how do you explain the fact that you can take 8 protons which don't want to be near each other because they all have the same charge, but yet you force them together and they become very stable. Then you have the electrons that are, so here's this nucleus, okay? So you have these 8 protons that don't like each other, okay? That's a problem. And then you've got the 8 neutrons, okay? And I know that because remember, and again, I'm just making sure everybody's cool. Remember, this is your relative atomic mass. And on your relative atomic mass, each proton and each neutron has a relative atomic mass value of about 1, okay? If you go far enough out, there's actually a slight difference in those, but for what we're going to do, protons and neutrons each have a relative atomic mass value of 1. So when you look at that in terms of being 16, what that tells us is that the most common atom of oxygen has 8 protons, because I know that, and then 8 neutrons. And so that's how we get that 16. But when you look at this, remember this is like an average. So what that tells me is that, let's say for example, we have the first quiz, and there is 18 possible. And the average score on that quiz, I do the numbers and it's 16, okay? 16.000. What that tells me is that about everybody probably scored pretty close to 16. Now, if I say, oh, the average is 16 and a half, that means that there was some variation. Maybe a lot of kids scored 16, maybe some of them scored 17. So when you look at your relative atomic mass values, like let's say, for example, chlorine. Chlorine is 35.5. So what that tells me is that there's obviously a high abundance of different isotopes of chlorine, because that's like it's halfway in between a couple of values, like 35.5. Maybe a lot have 35, maybe a lot have 36, maybe there's 35 and 37, something like that. So when you look at those relative atomic mass values, that's an average. So if you, like, let's say, for example, you look at magnesium. Magnesium is 24.3, okay? So that tells you that there's probably different isotopes of magnesium. Ones we're going to use most often are going to be oxygen, which is 16, carbon, which is 12, hydrogen, 1.0. Those are the ones we'll use most often. So when you're doing mass calculations, always go out to at least the 10th. So like when you're dealing with chlorine, don't round chlorine to 36, don't round it down to 35. When you're doing mole calculations and that type of thing, go out to like the nearest 10. So if we go back to oxygen, so we have 8 protons, we also have 8 neutrons. But yet, these are very stable. And so when I walk in each morning, and I've been teaching in this district since 1993, well before you all thought about being on this earth. I've had this table since the fall of 1994, okay? I've had it for quite a while. So when I walk in every morning, there's a lot of things that I worry about. What I don't worry about is I walking in and then all of a sudden my table has changed into a squirrel, okay, or something like that. So whatever, like, what have my table? It's a squirrel. Really? Cool, okay? So I've taught behind this table for a long time, and it's very stable. So whatever atomic theory that we have, it has to be able to explain the stability of atoms, okay? You all don't have to worry about waking up tomorrow morning and like half of your atoms have changed from like nitrogen into carbon or something weird like that, or all of a sudden half your atoms start to split into something else. It's like, what happened? Mr. Burkham, I don't know what happened, so I can't make it to class today. I went through a fusion process. Really? Good for you. Okay. So we don't have to worry about that. They're stable. But the problem being is that, you know, what I just demonstrated with that balloon and that piece of plastic is that they don't want to be near each other because they have the same charge. And so what happens is they came up with what's known as called the strong nuclear force. The strong nuclear force is what holds protons and neutrons together. It's the strongest force. That's why we call it the strong nuclear force. Catchy name, I know. But that force holds the particles in the nucleus together. And if the strong force didn't exist, we would never be here having this discussion. So thankfully, the universe not only created gravity, which allowed the fusion process to happen, the universe also has this strong nuclear force. And without the strong nuclear force, we wouldn't be here having this discussion because you could never form a nucleus because the protons would never want to get near each other. So you got these 8 protons. Now, we got 8 electrons. So again, let's go way back. When we talk about electron configurations, the S, the P, the D, the F sublevels, okay? Is that at least somewhere blocked in your brains? Okay? Hopefully, we've never seen those before. That's problematic, okay? Hopefully, you've seen S, P, D, and F. And if you're not sure, here's your periodic table, okay? And these first 2 columns, remember, here's your alkali metals, okay? And then you have your rare earth, and then you have your transition metals, and then you have your non-metals, and then you have your noble gases, and then you have your halogens. Okay? So, quick refresher. The S sublevel, that's the simplest of the sublevel. Again, Mother Nature's a lazy prima donna. So the S sublevel is the simplest, that's a spherical. So when you look at a nucleus, like I imagine you have an X and Y, Z axis. So here would be your nucleus, and your S sublevel is this spherical region. Now here's the other thing about electrons. We really don't have any idea what they're doing. We really don't. I spend an entire class talking about electrons and how they interact. We actually don't have a clue where they are. I said, well, that's kind of weird. Try teaching it. Anyway, to teenagers, it's like, really? Just accept it. So one of the things you'll realize when you get into the study of like quantum mechanics and what happens on an atomic level, the worst thing that you can try and do is to try and overlay a macroscopic reality on what happens on an atomic level. You can't, okay? If you do, here's what's going to happen. True story. You're going to end up doing drugs, and you're going to end up being in the back corner in the fetal position sucking on your thumb all day. Bad things are going to happen. So, I mean, Einstein even struggled with it, okay? Einstein hated the idea of quantum mechanics because his famous quote was that I can't believe that God rolls dice. And so when we talk about what electrons are doing, it is a beautiful mathematical model. It works. It's magnificent. But we really don't know what's happening. Okay, we make some observations, but I can't show you, oh, here's a single electron. Can't do it. Okay? And we'll talk about regions of probability like this S sublevel. All we can talk about is where it's most likely to be found. Okay? It'd be like, okay, it's 20-1, highest degree of probability. Gracie's going to be at that table. Okay, 20-1 in the afternoon. So if you consider, here I am, and we look at a probability distribution, the highest degree of probability where Gracie is going to be a certain distance away from me. Now, eventually we're going to do labs, and then, okay, hey, Gracie might be over there in the lab area, okay, so there might be a smaller probability distribution over there. You could go to Paris, France, at 20-1 in the afternoon. Gracie might be in Paris. I'm not saying that she can't be, but that's probably a literally low probability distribution that Gracie's going to be in Paris at 20-1 in the afternoon. Okay? So the same thing happens with electrons. If here's the nucleus, as you move away from the nucleus, we're going to hit regions of highest degree of probability. In other words, this is where these electrons are most likely to be. We don't know for certain, okay, but we can just say this is where they're most likely going to be. And then, so this is like your first energy level, so this is going to be 1s2. So if we were to write the electron configuration for oxygen, we have 8 electrons to account for, okay, 1s2. So again, one of the things you've got to be able to do is use your periodic table. So up there at the top, you have 2 elements. You have hydrogen and helium. Oh, there's a 1 out there. That means that you're occupying the first energy level. Oh, 1s1, 1s2, simple. Now, you move down and you start with lithium, okay? So that's the second row going across. So that tells me that those elements in that row are going to have electrons in the second energy level. Oh, so then we're going to go to 2s2. And if you're not sure, go, God, I don't remember how many electrons are in an S sublevel. This is your S block. Count the columns. Oh, there's 2 columns. So that means that starting with lithium, sodium, potassium, all of those have an S1 electron. Okay, it's one single electron out there. Okay, cool. Then if you go across, then you have S2. Oh, there's 2 electrons in that energy level. Then you come over here and you hit the P block. Okay, well, if you go over there, there's 6 columns. Oh, there's 6 columns because there's 6 electrons in the P sublevel, and in that there's 3 orbitals. So remember, in the P sublevel, there's 3 orbitals. Each orbital can hold at most 2 electrons. So if you go over here, we're at 1s2, 2s2, and then we go 2p4. Now, again, I'm just to make sure everybody's cool. So there's a couple of different ways you can represent these electrons. One of them is that you can do the orbital notation where you draw your orbitals and you show where the electrons are. So this would be like 1s, and there's different ways that you can do this depending upon what you want to do. Some people will put x's, okay? Oh, it's an x because it can hold 2 electrons. And then you got 2s, there's this one, and then you have 2p, The P sublevel has 3 orbitals, each one can hold 2. So you come in here and you put 1 in each one. You put 1 in each one because these electrons don't like each other. So it's like, oh, we have 4 of them. Oh, let's put all 4 of them in the same sublevel. No, Mother Nature goes, no, not happening, okay? They don't like each other. They want to repel each other. So this is why you put 1 electron in each orbital. Then once it gets filled, then you start to put, then you go back and then you start to backfill, okay? Sometimes you'll see it written as arrows, like an up arrow, and then you come back and you put like a down arrow, okay? I don't care which one you do, makes me no difference. Technically, the arrows are more correct because you talk about spin. Like an electron could have like a spin like this or an opposite spin. We really don't know what electrons are doing, but we know it has something to do with angular momentum. Because again, we can't see an electron. We can't see an atom, let alone see a single electron. But we can figure out what it's doing by observing the light that they emit. Okay, so that's one way you can do this. You can also do the Lewis dot. Okay, remember in the Lewis dot, you find the highest occupied energy level. So you can think of this as, some people like to think of this as being like a rectangle, and you can put at most 8 electrons around there. So you come up here, oh, there's a total of 6 electrons. So you go 1, 2, 3, 4, 5, 6. Now, anybody remember the law of octets?
Electrons want to go to their 8s.
Yeah, they want to have 8 electrons because oddly enough, that's the most stable form. And so basically oxygen is sitting there and going, hey, we've got 6 valence electrons. So after I graduated from K-State, I taught in Africa in the Peace Corps for 2.5 years. And when I was teaching chemistry there, all the kids came from a rural background. They all grew up herding goats. And so I would explain atomic structure in terms of goats. And I said, hey, everybody wants to have 8 goats because that's cool when you get 8 goats. And I would say, you have 6 goats, what are you going to do? Teacher, we will go get 2 goats. I said, that's what oxygen does, okay? Oxygen is missing 2 goats, so it goes and gets 2 goats, okay? Now, the halogens have 7 valence electrons. They have 7 goats. How many do they want? Teacher, they will go get a goat. I said, yeah, they will go get 1 goat. They're cool. I said, but what if you already have 8 goats? Teacher, we don't need more goats. We have 8. That's fantastic. So that's what happens with the noble gases, okay? Neon, all of those, okay? They don't interact with other electrons because of the fact that they have 8 goats. And they're cool, and so they're snobs. And so, you know, helium, neon, whatever, they go up to the other atoms, other atoms go, hey, you want to interact? And they go, I don't think so, okay? They're snobs because they have 8 goats. They have the most stable electron. And again, Mother Nature is a lazy prima donna. So oxygen, sulfur, they have 6 valence electrons. They become more stable when they gain 2. That's why it does that. If it became more stable by gaining 3 electrons, they would gain 3 electrons, but it doesn't. 8's the magic number. Halogens have 7. Gains 1. There you go, because it becomes the most stable arrangement. Now, you look at the alkali metals, lithium, sodium, potassium, those all have 1 valence electron. So I'll spend a lot of time explaining stuff in terms of electrons named Timmy, okay? So basically what's happening is that you have Timmy, which is this 1 electron. So if you look at like lithium, that's sodium. Let's do sodium. So sodium has 11. So it has 2 electrons, and then it has 8. And then it has this 1 lone electron way out there on the outside, okay? So Timmy's out there all by himself, okay? It's a long way from the nucleus. They have opposite charges, so they're attracted to each other. And basically sodium's going, Timmy, you are such a pain, right? And so it's like you're out on a date and you have to take along your little brother, all right? And it's like, Timmy, you are such a dweeb, okay? And somebody comes along and says, hey, can we have your little brother? Take him, he's out, okay? So you're going to sell Timmy down the street in a heartbeat, mainly because what's going to happen is that then, once you get rid of Timmy, now you look like a noble gas. You look cool. So sodium wants to become like neon, okay? So it gives away an electron, because then it looks like on the outside, it looks like it's neon. It's not, because it still has 11 protons. So it appears, in terms of electron structure, to be neon, but it's not, because it still has 11 protons. But it does that so it becomes more stable. So basically what happens there is like, you're trying to herd the goats, you have 11 of them, and one's always running off, and someone comes up to you and says, hey, can we have that last goat? Let's take it, okay? I'm tired of dealing with it. So Timmy the goat, he's out, okay? So this is why you have the formula sodium chloride. It's NaCl. Sodium has one excess goat out there in that third energy level. Doesn't want it. Chlorine's sitting there. It has 7 goats. It needs 1 more. It's a match made in goat heaven. So sodium goes, hey, take Timmy, the goat. Cool. We'll become more stable. Chlorine's happy. Winner, winner, chicken dinner. It becomes the most stable arrangement. Okay? And that's why it's NaCl. There you go. So if you view chemistry from that perspective, that's why it does what it does. Okay. Now, let's talk about relative atomic mass. So if you look at the history of chemistry, and we screwed some things up along the way. The first thought was that they actually had like 4 elements. These were the Greeks. You had water, air, earth, fire. Okay, chemistry is pretty simple. Okay, you had 4 elements on your periodic quiz. Okay, pretty simple, not a big deal. But that was cool philosophically, but it didn't really work. So one of the things they started to do was they said, okay, well, let's look at relative atomic mass. So when you look at relative atomic mass, and this is going to be important, atoms are so small when they were coming up with this idea of relative atomic mass in the 1800s. They didn't have the capacity to measure the mass of a single atom. Okay, they didn't know what it was. They just couldn't measure it because it was so small. They said, okay, we don't know the mass, so we're just going to make up a number. So they said, okay, what's a simple number to work with? Oh, 1. Oh, hydrogen's abundant. That's the lightest element. We're going to assign that a relative atomic mass of 1. They could have assigned it a relative atomic mass of 10. They could have called it pi, whatever, okay? Let's just make this simple. Let's just call it 1. Okay, cool. So then they looked at carbon. Carbon's also pretty simple to get pure samples of carbon. You want a pure sample of carbon? Take some green beans. I don't recommend that you do this. I'm just saying you could do this. Take some green beans, throw it on the stove, okay? Cook it until it turns black, charcoal, basically. You have pure carbon. That's it. Okay, it's easy to get pure carbon. So that was relatively simple. And they said, hey, let's compare these values. Oh, right. If you set up a balance beam and you put 1 carbon atom on one side, over here you would have to stack up 12 hydrogen atoms to balance out 1 carbon. Ah, right. So we'll assign carbon a relative atomic mass of 12. Simple. Okay? It's a relative mass. This is going to be important. It's a relative mass. Okay? It's not an absolute value. So when you see oxygen as being 16, it's a relative value of 16. Okay, cool. And I said, okay, but here's the problem. We're not going to measure, if I'm not going to go to the lab, I'm not going to go to Leslie and go, hey, Leslie, I need you to measure out 1 carbon atom. Okay, it's not going to happen. She's going to get a spoonful of it, right? I said, okay, well, what can we do? And I said, At the time, metric system was all the rage. And they said, okay, so instead of having carbon with a relative atomic mass of 12, instead of putting atomic mass units on the end of it, we're going to call that grams. They could have picked, so when I give this lecture, in physics, instead of a mole, it's called a kilomole, which sounds weird. Peter doesn't like that. It's a kilomole. It's like, you're killing the moles? No, it's a kilomole, not a kilomole, okay? It's a kilomole. So in physics, 1 mole is 12 kilograms, okay? In chemistry, a mole is 12 grams because they work off of the gram system. So then that was a cool idea. Grams, okay. They could have picked pounds. They could have picked ounces. They picked grams. Okay? Because at the time, the metric system was all the rage. All the cool people were using the metric system. Okay, we'll use that. So then, the next challenge became, well, how many atoms are there? Okay? In there. And so this is where Avogadro comes along. Avogadro says, and Avogadro never came up with a number. Anybody remember Avogadro's number? And no, you don't get to answer the question.
6.02 times 10 to the 23rd.
Fantastic. 6.02 times 10 to the 23rd. Okay? And so how they got that number is they said, okay, I'm going to take a balance and I'm going to start stacking carbon atoms. Okay? And I'm going to put carbon atoms after carbon atoms after carbon atoms after carbon atoms. And I'm going to keep putting carbon atoms in here. Okay? And the pile is going to get bigger and bigger and bigger and bigger and bigger and bigger. And I'm going to stop when the scale reads 12.0 grams. So when I reach 12.00 grams, when I put that last carbon atom on there and reads 12 grams, not 12 kilograms, not 12 pounds, not 12 ounces, 12 grams, we're going to count how many atoms are in that bucket. And it's 6.02 times 10 to the 23rd. Okay? Because that's how many atoms it takes to equal the relative atomic mass in grams. Now, you look at water. Okay, cool. Here we have water. Okay. H2O. Okay? Relative atomic mass of water, H2O, is 18 grams per mole. So the same thing happens here. Oh, okay, right. I want to take a pan balance. I want to begin to chuck water molecules on here, water molecules after water molecules. And I'm going to stop when it reads 18.0. Oh, that's still going to take 6.02 times 10 to the 23rd. So the cool thing about Avogadro is that he proposed this idea, but he never actually came up with the number. He left that to someone else. So when you talk about Avogadro's number, it's an important number. Remember, that's the relative, because it takes that number of particles to equal the relative atomic mass in grams. In physics, Avogadro's number is actually 6.02 times 10 to the 26th, because we talk about kilomoles. And so instead of 12 grams, it's 12 kilograms. Okay? And remember, there's 1,000 grams in a kilogram. So in physics, it's a kilomole. And Avogadro's number is 6.02 times 10 to the 26th, because we have to get to 12 kilograms instead of 12 grams. So the number is kind of arbitrary. But that's what I want you to remember, is that Avogadro's number, the reason that it's 6.02 times 10 to the 23rd, is because it takes that number of particles, added up, and you combine all that mass to get the relative atomic mass in grams. Okay? Cool with that. Moles. Well, let's talk about moles, right? So 1 mole is relative atomic mass expressed in grams. It contains Avogadro's number. You can also roll that into molarity. Okay? Molarity, what's another way to express molarity? No. You've used your quota. Moles per liter. Okay? That's moles per liter. So for example, here I have 1 molar sodium hydroxide. So what that means is if you have a liter of this stuff, within this you would have 1 mole. If it was a 2 molar solution, you would have 2 moles per liter. But remember, when I mix this up, I can't measure in moles, I measure in grams. So if were I to mix this up, I'd have to measure out 1 mole. Now, let's talk mole conversions, because we're going to do those a lot. So let's say, for example, I want to make a 2 molar solution. I want you to measure out 2 moles. So here's how I want these done. I want to convert 2 moles of sodium hydroxide into grams of sodium hydroxide. So remember, whatever units you have here is what you put down. There's no variation to this theme. There's nothing to think about. If I have moles of sodium hydroxide, I put moles of sodium hydroxide down here. Now, at this point, you're going to go to the periodic table. Molar mass of sodium is 23, oxygen is 16, hydrogen is 1. You add all that together, you get 40 grams per mole. So that's 40.0. The mole is going to cancel out. I get grams of sodium hydroxide. So that becomes 80.0 grams of sodium hydroxide. Okay? Everybody cool with that factor label method? One of the things that you'll hear me preach again and again and again and again and again is that I worry about the answer to a certain degree, but I also worry about the process, okay? So make sure you show your work. Also, on the list of things that irritate me, do not write in pen, okay? Oh, I will have no tolerance whatsoever, okay? None. It's like, don't sit there and go, I don't like to write in pencil. I don't care. And that's true, okay? It's true, I don't care. And it sounds egotistical, but your job is to make me happy, and the happier I am, the better your grade is going to be. There's also an inverse relationship between my blood pressure and your grade. So if I'm grading and my blood pressure goes up because I'm frustrated, what's going to happen to your grade? It's going to go down. So you want to keep my blood pressure low and your grade high, because if my blood pressure goes up, your grade goes down, okay? That's the cold hard reality of life. All right, so let me hand this out. Just keep that going. That review assignment. Here's what I want you to try and do. I want you to try and work.
That's what I needed.
Oh, okay. So this should be a review of everything you've learned in Chem 1 and Chem 2. So do not flip out if you come to some of those and you go, I have no idea how to do this. So I'm basically going to spend tomorrow working through this to make sure we're all starting off on the same footing, okay? So if you come across some of those and you go, God, I don't know what this means, don't flip out, okay? Actually, I prefer that I need to know what you know and what you don't know so that I can begin to tailor this towards that wave. I need to figure out where I need to put that wave. So, you got the periodic table, you've got your list of cations and anions, you have the solubility chart. There you go. So we will spend tomorrow going over this, so hopefully this will tell you what you know and what you don't know. So, okay, I'm done.